Okay, let's start. So today we will continue to have a lecture. And this is also a warm up for you. I hope you made some progress on your project so that you can realize that whether your project, the goal of your project is realistic or not. If you have any question about the project, you can ask me at the end of this lecture. In this lecture, we will talk about SRAM and cache. Although we have some memory element we introduced some memory element in the circuit. Now we will talk about the memory array, the larger memory component. So you can see that compared to the CPU, memory becomes more and more slower. The y-axis here is the performance. For example, the instruction per cycle. The higher, the better. And the x-axis here is the age. With the development of process technology, architecture innovation, CPU becomes more and more faster, becomes much faster. But the memory has a little improvement. Particularly now you have a multiple core, multiple applications running on the same machine. Then the memory becomes even slower. Although we have a latch, flip-flops, these are very expensive because in one latch or one flip-flop, you can have a lot of transistors. Although they are very fast. So we have to build a storage hierarchy or memory hierarchy to use not so expensive memory component, but provide a very short latency or faster speed. Then this is our hierarchy, no matter you call it memory hierarchy or storage hierarchy. On the top of the hierarchy, of course, these are latches, flip-flops, registers. They can be integrated into the computing unit, for example, an adder or a multiplier. And then we have a cache. Cache is actually memory array, SRAM array particularly. And then we have DRAM. You can actually buy some DRAM online and insert into your PC. So you can upgrade the capacity of the DRAM in your PC, in your own computer. So, but you can never do that for the cache because the cache is the memory array integrated into your CPU. And then we have a SSD flash. And then we have a magnetic disk. For example, 8 terabytes disk. It's very common now your computer have both disk and SSD, particularly for your laptop, desktop. The registers, cache, and the memory, DRAM, are managed by the hardware. But the SSD and your magnetic disk are managed by the operating system, which is a software. you cannot do some programming to change the policy in DRAM or in SRAM or in registers because they managed by dedicated controllers like the finite state machine we talk about in previous lectures. In this memory hierarchy, the topper level, higher level has a smaller capacity but a faster speed. The bottom level has a lower speed but a larger capacity. Because your application has a so-called spatial locality or temporal locality, the most important component of your application or the most important data kernel can be cached in the register or the cache or the DRAM. So in this way, we can enjoy both the faster speed and the larger capacity. Meanwhile, we don't have to pay maybe 8 terabytes registers. We don't need that. We just maybe need a 64 kilobytes register. That's totally enough for your applications. And this is all because we have a memory hierarchy for that. And in this lecture, we will focus on the cache, the SRAM. Again, the cache is managed by the hardware. You cannot change the policy in the cache. The cache will divide the entire memory into blocks. Each block costs several bytes. For example, 64 bytes. Each time the cache reads 64 bytes from the memory, and your CPU read maybe also 64 bytes from the cache. So in this way, you can capture the spatial locality. And we only keep the most recently used or most recently accessed blocks in the cache. So in this way, we can capture the temporal locality. So here are some concepts about the cache, which are blocks, frames. Blocks is the minimum unit that can be cached. Frame is the physical location, memory location, actually hold one block. If you can find one particular block, that's so-called a hit. If you cannot find, then it's a miss. Of course, we have a miss rate, hit rate, and the time to access one block is the hit time. If we have a miss, the time we need to replace a block, that's so-called a miss penalty. Don't worry, we will explain each concept in the following slides one by one. So assume we need to sequentially access 6 blocks. In this example, we assume that each block or each line is 8 bytes. So these are the lines we need to access. When we access the first line, of course it's a miss because we have an empty cache. It has nothing in it. So you cannot find that. When we try to access the second address, if we have a miss, then we need to fetch that block from the memory. and fill it into the cache. And then we can go to the second address, try to access the second address. Then fortunately, we get a hit because the second address is included in the first block, because the first block contains 8 bytes. When we try to access the third, we have a miss. We fetch the line from a DRAM and then write it into the cache. When we try to access the fourth line, then it's also a miss. We fetch the line from a DRAM and write it into the cache. We try to access the fifth line, then we have a hit. And the last line, we have a hit. So in this way, we have 3 misses, we have 3 hits. So the hit rate is 50%, and the miss rate is also 50%. Here we need to introduce an equation to compute the speed of your memory access, of your cache access. Assume if you can find your block in the cache, that's a hit. A hit costs you 10 cycles. If you cannot find that block, that's a miss. A miss means you need to access the DRAM, the memory, which costs you 100 cycles. With a different hit rate or miss rate, you have an average access latency. You can compute that in this way. This is the hit rate. This is the miss rate. Miss rate equals to 1 minus hit rate. So you can see this is the hit rate. This is the miss rate. This is the miss rate, and this is the hit rate. With a larger hit rate and a smaller miss rate, we can significantly reduce the average memory access latency, which means that the memory is faster. So it's critical to improve the hit rate in the cache. In order to improve the hit rate, we can integrate more levels of cache, because we have a hierarchy in the storage or in the memory. We can add a L2 cache. So in this example, the L2 cache cost your 20 cycle, and L1 cost your 5 cycle, and the memory still cost your 100 cycles. So if we have a 20% miss rate in L1, 40% miss rate in L2, this is how can we compute the average memory access latency. Because the miss rate of L1 is 20%, so 80% will hit in the L1. And this is the L1 hit latency. For the other 20%, this is the miss, okay? For these 20%, among these 20%, 60 are hit in the L2. And among these 20%, 40% will go to the memory. So this is this part. On average, we need 14 cycles to access the memory. Either you can reduce the miss rate, or you can integrate more levels of cache to reduce the average access latency. So this is the typical memory organization for one single core. We have a register, we have a separate cache, L1 cache for data and for instruction. We have a unified L2 cache. And we also have a very large L3 cache. And we also have a memory, DRAM memory. Now, I think almost every CPU has multi-core. Even your mobile phone has more than one core. So this is the case for multiple core. Each core have a private L1 cache and L2 cache, but they share the same L3 cache. And you can think about this case. If you run some data analysis on one core and you watch YouTube on another core, then the data analysis core may need a larger capacity of your cache. So it will, use up this L3 cache, and your YouTube core cannot have any space here because this L3 cache is shared. So in this way, in order to improve your so-called user experience, you need some scheme or some mechanism to keep some space in the L3 for your YouTube core. So we do need some coordination in the L3, in the shared resources, to keep every core busy or fully utilized. Otherwise, some core has a very memory-intensive workloads will dominate the L3, and the other core cannot use them at all. So this is a chip layout for the Intel CPU. So you can see that on this CPU chip, most area, I can say maybe 50% of the chip area is occupied by the memory. Even inside the core, we have a lot of memory components. So compared to the other parts in the chip, the memory layout is a very regular. You can see, you can even point out which part is the memory by just looking at this chip. But other logic here are not so regular. So the cache is actually made up by SRAM. This is one example of SRAM. The SRAM structure, one cell of SRAM is very simple. It's just, there are two inverters. The input of one inverter is connected to the output of the other inverter, like this. So in this way, it can achieve a very stable state if the output of this inverter is 1. Because this is also an inverter. We have a 1 here. This is the input, the output is 0. So you can see this is a very stable state. You can change this 1 to 0 here, and then this is 1. It's also another stable state, like this. Besides 2 inverters, we also need 2 transistors to control this cell. This is the component we can sense the content in the cell, and by these 2 transistors we can connect this cell to the sensor, or we can disconnect the cell from the sensor. We need to control here. So in this way, we call it, because each transistor, I'm sorry, because each inverter has two transistors. We have two inverters here. We have totally four transistors. We also have two control transistor. So totally we have 6 transistors in one SRAM cell. This is so-called 6T SRAM, 6 transistor SRAM. So we can organize the SRAM in this way. We can connect all the control to one horizontal line. If I send a 1 to this horizontal line, then all the cell will connected to the vertical line, which means that we can sense the data from the cell through these vertical lines. But all the control is managed by this horizontal line. We call the cells who managed by the same horizontal line a row. And the horizontal line itself is called a word line. And the vertical line is so-called bit line, because we can sense the cell bit by bit, sense the cell one by one, bit by bit. Each cell represents 1 bit. And we can also organize the cell like this, like in one array. So the horizontal line named word line, and the vertical lines too are called bit line. And we will have no conflict between different word lines, because each time we just enable one word line. So in this way, only one row of the cell are connected to the vertical bit lines. Although, all the rows share the same word lines. Each time we only enable one word line. So in this particular example, this row is enabled. With the memory, we can organize them into caches. So this is a typical cache. We have a tag, we have a state, we also have the data area to record the data. So the simplest cache and the most powerful cache is the fully associative cache. The fully associative cache means, your data can store in anywhere, in any frames of this cache. So each time, in order to find your data, the tag is your data address. In order to find a piece of data, because your data can be stored in any frame in this cache, in order to find your data, I need to compare all the tags against the data's address you are looking for. If I get a hit here, then you can have your data. Otherwise, you have a miss. So there are 3 common miss cases. One is a compulsory, which means you have a very cold cache. Your cache is empty. You have nothing in the cache. So during that time, you always have a miss. The second one is a capacity. Because of your limited capacity of your cache, you have a miss. And the third one is a conflict. Conflict means conflict. Conflict means it's not a compulsory miss or capacity miss. I will talk about this type of miss in the following slide. And the last one is not so common, but we do have such type of miss, is the coherent miss. Coherent means multiple cores share this piece of data. Once some core modify this piece of data, then you have to invalidate the copy of this piece of data in other CPU caches. So the capacity, the cache size, the block size have a huge impact on the miss rate and the hit rate of your cache. So the x-axis here is the capacity. The y-axis here is the hit rate. So you can see that when you try to increase your cache capacity, you can increase the hit rate, of course. But when you increase the capacity of your cache to some threshold, like here, the hit rate just saturate. This is because the cache now is larger than your application's working set size. Further increase the capacity does not help too much. But if your cache size is smaller than the working set size, then the hit rate significantly decreases. Block size means one frame, the size of one frame of the minimum unit size you read from DRAM to cache and from cache to your CPU. So the y-axis here is the hit rate. The x-axis here is the block size. So you can see when you increase the block size, at the beginning, the hit rate increases. Each time you bring more data from the DRAM to the cache, this is good because you have some spatial locality. For example, if you want to access one array, when you try to access the first element in the array, then each time the cache may read 4 elements, consecutive elements from the DRAM. The next time you want to read the second, then you can have a hit directly. This is so-called, why a larger block size can help your spatial locality. But again, if you have a too large block size, you bring a lot of wasted data, the data you will never use. For example, if you want to access the array, it's very likely for you to, after you access the first one, it's very likely for you to access the second one. But if you bring the entire array in the cache, it's pointless. You may not be able to, traverse the entire array in the cache. Maybe you just need the first 4 elements. In order to build a cache, we also need a decoder. The decoder can help you to select only one row in the array. Only you sense all the data from one row. Sometimes you need just maybe 1 bit or several bits in it. So you can use another decoder to select these bits. You don't have to read them all. You can select some of these bits. So the whole process will be when you decide to access a piece of data, you first active its row, its word line. And then the array will sense all the data onto these sense amplifiers from its bit line, vertical lines. I mean, all the data. But you don't have to transfer all the data out of this array. You can only you can select only a part of the data, several bits, by the bottom decoder. So the fully associative cache is very good. You can store your data in any location of the cache. But the problem is that when you look up the cache, you have to compare all the tags. Potentially the lookup will be very slow if you have a very large cache. A larger cache means you have a lot of tags to compare. You cannot compare so many tags in one cycle, which means that the heat latency will be prolonged in the fully associated cache. Sometimes you just need some faster lookup. And you may want to sacrifice the heat rate. And then we have a so-called direct mapped cache. Direct mapped cache means that your data can be only stored in the location it allows. How to evaluate whether you allow this piece of data in this location or not? We can give it a very simple equation. We use the mode equation to do that. For example, if this cache has 8 frames, then you just need to use your data address to mode this 8. If you want to read address 0, it will be stored in location 0. 0 mode 8, which is a 0. You only have one possible location by this equation, by the definition of this equation. If you want to read address 1, then you just use 1 to mode 8. You go to location 1. Your data can be only in location 1. If location 1 has no your data, then you have a miss. If it has your data, then you have a hit. In this way, the comparison is very fast because you only need to compare only one tag. But the problem is that, okay, address 1 is stored in location 1. Address 9 is also needed to be mode by 8. Then the answer is also 1. So the address 9 and address 1 will have a conflict if both of them want to store the data in the cache, because they will be stored in the same location in the cache. So although we have a faster lookup time, faster lookup operation for the direct mapped cache, we will have some conflicts in the direct mapped cache. Then this is the trade-off. For fully associated cache, you have a larger flexibility. It's more flexible for you to store one piece of data to any location of your cache. The hit rate will be good because you have more opportunity to store your data. But unfortunately, the lookup time is longer. For the direct mapped cache, the lookup time is shorter. But potentially you have more conflicts, which means that the hit rate will be low. Which type of cache is good, is better for your application? Then you need to do the sensitivity study yourself. So here is one example of the conflicts. Although they have a different addresses, the addresses here are different. They have the same index. The same index means these addresses fight for the same location. These are so-called conflict. Although even other locations are totally available, totally empty, totally free, you cannot use them in the direct mapped cache because these addresses are only allowed to fight for the same location by the equation of the mode. Then some people try to, try to combine this direct mapped cache and fully associated cache together. That's the reason why they propose a new cache organization, which means which is actually the associativity. So they propose a cache called the set associative cache. At the top level, the set associative cache is so-called direct mapped cache. You have 4 sets here. After you have your address, you just do mode 4. If you have a address 0, then after mode 4 you have a 0. Then you go to the set 0. Inside the set 0, you have 2 choices. Inside one set, you actually have a fully associated cache, and you have 2 locations. You can store your data in any of them. So in this way, you just combine the direct mapped cache and a fully associated cache. At the top level, it's a direct mapped cache. At the bottom level, at the second level, it's a fully associated cache. So in this way, you can enjoy both the flexibility and the shorter lookup latency. When you increase the set associativity, you increase the location inside one set, which means that you have a larger fully associated part in the set associative cache. So the hit rate will be better. But again, during each time, you have to compare a lot of more tags, then the power consumption is larger. So with a larger set associativity, you set associative cache is more like a fully associated cache. With a smaller set associativity, your cache is more like a direct mapped cache. So the y-axis here is a hit rate, and x-axis here is the set associativity. Again, when you increase the set associativity to some threshold, the hit rate just becomes saturated. This is one example of the set associative cache. This is so-called two-way set associative cache. And each array is one way. Each horizontal line is one side. With different sets, we have a different cache replacement policy. When you have a miss here, then you just need to replace the cache. We can use the least significant, least recently used, not most recently used random pseudo LRU to do the replacement. And although some people create some algorithm to claim that they can have an ideal replacement algorithm, but the overhead is too large. So the ideal replacement is never implemented in real CPU. Any question about cache? Any question about the project 2? I'm sorry, the project 2. About the presentation. Then next Monday, we will do the second presentation on our project. So if no more question, we can stop today. Thank you very much.